Okay, now we are going to apply Newton's second law to polar coordinates, which the equations of motion are pretty straightforward. We've seen these for other coordinates. It'll just be the sum of the forces in each of the directions equal to the mass times the acceleration in each direction. So I have my radial direction, my transverse direction, and then my z direction if I have cylindrical coordinates. So again, nothing too surprising there. The one thing we do need to consider is how the normal and tangential forces relate to these polar coordinates. So, for example, if I'm following a curved path that I have in polar coordinates, okay, oftentimes the normal force and the tangential force are of importance to us. That is, I may have friction, or I may have a force keeping me on the path, okay, which are normal and tangent to the path, which are different than the radial components, basically my r and my theta. Now, when I draw my free body diagram, okay, the angle between my tangent axis and my radial axis becomes important. Knowing the angle between, these normal and tangential forces with the r and theta axes that I know my acceleration to be. Okay. So again, here's this red line is my tangent axis. Okay. This line extending right here is my radial axis. Okay. So I'm finding the angle between the radial axis and the tangential axis. Okay. So in order to do that, I have this little triangle right in here. Okay. That I'm looking at, and if this is blown up, but if I shrink it all the way down, okay, I can treat this line right here as ds. That's basically the distance that I move on the path. Okay, again, this is blown up, but if you shrink it down to approaching 0, that's what that leg of the triangle represents, is the distance along the path. Okay, this line right here is basically an arctangent of me making a circle. Right? If I move some angle d theta, some fixed distance r away, that distance right there is going to be r d theta. This little angle right here is the total r plus the change in r. Right? So from here to here is just dr. That's the change in r. It was here, now it's there as I move up to this new position. So I've got this little triangle here. Okay, this angle right up here, because of the interior opposite angles, okay, this is my psi angle that I'm looking at. That's the angle between, again, my radial component and my tangential component. Okay, so that's essentially the tangent of, opposite over adjacent, where the opposite is r d theta and the adjacent is dr. Okay, so that's where that relationship comes from. Okay, now rearranging this just a little bit, basically putting d theta down on the bottom, I have the tangent is equal to r divided by dr d theta. That is, if I know, again, my path as a function of theta, right? R is a function of theta. That's basically what a polar coordinates gives me. I just take the derivative of that path with respect to theta, plug that in, I can find that angle through this relationship right here. Okay, so again, that's important when I'm drawing my free body diagrams, to know the relationship between, say, a normal and tangential force with a radial and transverse path, which I'm applying my equations of motion to, because that's how I know my accelerations to be when I'm dealing with a polar coordinate path.